Mhm. Okay, hello AJ.
Hi, can you hear me?
Yeah, I can hear you. You can see my screen, correct?
Yes.
All right, so maybe they are recording already, which is totally fine. How about I give you the screen so you can verify that you can post your slides and everything.
Yeah, that sounds good.
Mhm. Mhm.
All right, that looks good.
Yeah, that looks good indeed. Okay, good. Then I guess I'm gonna go back to showing all the. So what is on the screen right now? You can see the 4 people, right?
Right. Yep.
Okay. All right, it looks like just the 2 of us so far, but it's not 3 yet. We have 3 more presenters. They emailed me stuff, information. And a bunch of other people are supposed to show up as well.
Well, thanks for the invitation. I really appreciate it. I'm excited to talk.
Thanks for making time for us. I hope this is the right link. I hope people don't get confused. Sometimes they would, but. All right, so this is Tyler. Tyler is another presenter. Hello, Tyler. Can you hear me?
Hi, yes, I can hear you.
Let's make a little test. I'm gonna give you the screen, and why don't you share the screen.
Okay.
So to make sure that you can share the screen properly.
Okay. Let's see.
There's Carolyn also joining, and soon we should have Manuel.
How does that look?
Looks good. Mhm.
Okay, great.
All right, so we're now testing that that we can share the screen. So Carolyn, if you want to make a test that you can share the screen, I suspect everything will be fine, but just to be safe. Oh, beautiful. So the session is being recorded right now. We have a 4th presenter. I guess he's gonna join at some point. But we're gonna post this when it's over. So who's present? We have 3 presenters out of 4, and then we have the vice chair of the TAC, Terrell France, and then other people might show up. We'll see if the link is right or wrong or whatever. So the idea behind this is that if nobody shows up, which never happened before, then we should still do this and pretend we are on the radio, on a podcast, or on TV where you don't see your audience. And then this gets recorded, we post it, and then people will refer to this. Our goal is to join the e-poster sessions with the Quantum Marketplace. That is an event that runs every 2 months where companies come and they explain to all the other members what exactly they can sell. And they introduce each other and so on. So I think that the e-poster shows the talent that exists of people that are looking to maybe potentially join the industry, and the industry needs to consider that as well as the actual products that they're creating. There's also an office hour type of event where any student or postdoc, any kind of student can come and get a mentor from the industry. And oftentimes, if you go through the e-posters, they might look at or they might attend the video, the presentation, and then you already have, if you go to the office hour, you already have a mentor interested in you. So, Terrell, do you think we should start?
Sure. You know the protocol better than I do.
Yeah.
The important thing here is, getting the recording made. And so people refer to it later on anyway. So.
Right. So as far as I can tell, I don't know what I am. Well, there's somebody over the phone. I see 3 or 4 presenters, and there's Manuel. We have all the presenters now. So people might join, and usually do join while we are in the session. I have a feeling that it shows as if it is being recorded. I'm not host, I'm not co-host, but it doesn't matter. As long as this gets done, Mary Scott is going to give it to me, or Crystal or somebody, and then we'll post it. So before we get started, Manuel, can you confirm that you can share the screen?
Sure. Yeah, I think it's all
Very
good.
good.
Slides are there. Yeah.
So as expected, this is it. And so I think we should get started. I'm going to share the screen, and I'm going to tell you that on account that the recording is the most important thing, the amount of time that we usually have for these sessions is exactly an hour. With 4 presenters, we never ever have been able to finish in an hour. That's also important for the last presenter. So the goal is to have 15 minutes per presentation, including the questions and answers. Usually we have a significant amount of people, and then there are questions from the people in the industry. It just so happens that today we don't see as many people. And then I got some email messages from Jonathan and Celia saying that they would have wanted to be here, but they cannot. So it doesn't matter, they will watch the video. So having said this, we're going to get started. What's the time? It's almost 3:03, my clock over here. And then we're going to go roughly 15 minutes per person. If we end up into 4 o'clock our time, 4:15, so say up to 4:30, we'll end whenever we end. So having said this, I'm going to say that the screen shows the 4 presenters for today. This is session 17. It's Tuesday, January 24. And we have 4 outstanding presenters for our e-poster session. The first presenter is AJ Rasmusson, who is a doctoral student at Indiana University in Bloomington. He's in the group of Phil Risherm in physics. For all the presenters, I have a few things that I asked them. I'm just going to say a few words about him, and then I'm going to let him talk. So he graduated from Brigham Young University with a BS in physics in 2018. He's currently a PhD candidate in Indiana University working with Phil Risherm on quantum simulation with trapped ions. For the last 2 years, he has also interned with IBM's QED-C research team under Olivia Lanes, where he develops the Open Science Prize and other educational content for graduate level researchers. We have more information from AJ, but I think we should let him start. His presentation is entitled Quantum Simulation on Noisy Superconducting Quantum Computers. So share the screen and take it away, AJ.
Okay, thank you. Yes, thank you for the introduction. And today's presentation is on work I did with at IBM on quantum simulation. And before I get started, I wanted to also highlight that in this paper, we also put all of our code and every sort of plot that we've made on our Qiskit Research GitHub repo. So if you or you know someone that's interested in kind of like a graduate level introduction to quantum simulation, and they want to get more serious into kind of stepping stone into the literature, then definitely check out our repo. And we're really hoping people can build off of it, and especially people who are potentially new to the field of quantum simulation. So with that, we'll dive into it. So quantum simulation, this talk will be fairly general at first, then I'll get more specific. But in general, with quantum simulation, we have some sort of quantum system of interest. And here we have this beautifully rendered chemical compound. And we want to somehow emulate that with a quantum system we have a lot of control over, which, for example, would be a quantum computer. And how we do that is there's a lot of different ways to do that. For example, we need to know some sort of properties of the material and encode that in the quantum computer, and then execute some sort of simulation on the dynamics or find some observable you're interested in. And that then would inform us on what's going on in the material. much like classical simulation, but with kind of a quantum speed up is the idea. And of course, the details are where things get tricky. And so I'm going to go to explain just a brief overview of what it might look like to go from start to finish in a quantum simulation. And then I'll dive more into a specific example to highlight those different principles. So first, we need to identify a system, like I mentioned earlier, and decide what is it we actually want to measure about this system. And once we have that, we then need to translate that into the language that a quantum computer can speak, which for quantum computers, that's in terms of bits, like these block spheres I have here to represent qubits. Sorry, I said bits, but I meant qubits. And also poly operators, and such as like XYZ as I've written here. Once our system is encoded in this way, we can then actually execute some sort of algorithm on our quantum computer. And so that brings us to the simulation part. And within simulation, there's kind of three main components. One is state preparation, which can vary from very trivial to quite complicated. And that's a whole nother field and study. Then there's the time actual evolution. Here I've listed trotterized time evolution. That's a specific technique, but there are other ways to try to time evolve states. And then at the end, we want to measure our observable. And here I've written direct measurement to mean just measure in the Z basis and use that data. But sometimes observables, we might want some sort of correlation or different bases. And in our paper, we mentioned those other methods. And so if you're interested in that, definitely check that out. But for now, in this talk, I'll just talk about measuring the Z basis. You might think this is the end of the story, but obviously there's a blank spot in the bottom right slide, part of the slide. And that's because when you run this, if you did this and ran the quantum circuit, the data would not look very good. And that's where error mitigation comes in. Once we've set up how we're going to actually execute, we need to go back and pick some sort of strategy to mitigate noise and modify our circuit in some way to get the dynamics we want out, but avoid the noise. So the rest of my talk here, I'm going to choose a specific example, a toy model that will help let the quantum computing techniques kind of shine through of these different steps. And I'm going to kind of go fast through these first two sections and then slow down for the time evolution and error mitigation portion of the talk. So the example model that we picked was a tight binding model. And we just want to look at the state dynamics of some particle in this tight binding model. If you're not familiar with the tight binding model, that's okay. It's relatively straightforward. It's decomposed. It's in terms of individual sites, which here we're considering 5 sites, and they're coupled with a strength tau. We've also included the defect just to mix things up, which has a different coupling strength. You could abstract this to, or you could think of this as an example of maybe an atoms in a lattice. For example, this would be position, and at each site is a lattice or an atom with some potential, and then you have some electronic wave function, and then that's tunneling through this lattice, and you want to understand the movement of that electron. That's just an example of how you might, the specific model you might be thinking of. Now, we need to know what the Hamiltonian is for the system, and it's written in terms of second quantization operators here. So I'll first go through this first sum here. What we have is, this is called a hopping term because our C operators here, they will operate on a site, for example here, site I plus 1, and it will remove the electron, so to speak. And then the C dagger will then create the electron in a neighboring site. And so that's why it's a hopping term, because we move from one site to the other, or vice versa. And the second term over here is simply, we had to pull it out of the sum because we included this tau d to be different from tau. And this tau d could be something that models a disorder or something like that. And again, we've picked this to be some sort of as a fundamental model because although this model is relatively simple, we could quickly add on terms that turn it into a Hubbard model, or play with the couplings to make it more random to be some sort of many body localized model. But we wanted this to be like an introductory and a stepping stone for people to get into those more technical simulations. So how do we then do this Hamiltonian encoding into our qubits and Pauli operator space? Right, so we have our system in Hamiltonian, but we want it in terms of, right, these qubits and these Pauli operators. So what would this Hamiltonian look like? And there's many transformations you can actually do, and a very popular one is the Jordan-Wigner transformation. I'm going to brush over the details here, but feel free to ask questions if you have some later. What we can do is identify Pauli operator string here, where there's an implied tensor product. And we wanted this string to preserve the commutation relations between C and C dagger. And these relations do that. And when we apply that transformation, we find that our Hamiltonian can be encoded as an XY Ising model, sorry. And again, I kind of circled that as just an answer. We're going to skim past that so we can get to the next portion. So now that we have this Hamiltonian, we can do the actual quantum simulation part and figure out our error mitigation strategy. All right. In terms of quantum simulation, we need an evolution operator. Since the Hamiltonian is time independent, we can just say, all right, e to the IHT, and we have our unitary time evolution operator. Now this thing though, this object is a multi-qubit gate as it stands right now. It's operating on all 5 qubits, and there's terms in here that don't commute, which kind of make it complicated to work with. So how do we decompose this into 2 qubit gates and single qubit gates that a quantum computer might have available for you? And one technique to do this is trotterization. And I'm going to say trotterize, but that's a more informal word for the Suzuki trotter decomposition. And how the Suzuki trotter decomposition works is we can say, well, let's just evolve for a little bit of time. And in that approximative limit of a small amount of time, we can actually we're going to ignore some of the commutation rules that would normally apply, right? So here I've highlighted our four different operators in this term. And right now they're in this sum, but we're going to ignore kind of the commutation rules and split them into a product. And that's the approximation that we could do that. And what makes the approximation valid is, as I mentioned, we're going to only evolve for a little bit of time, a t over m, where m is an integer, and that's called the number of trotter steps. So as we increase m, this approximation is more and more accurate. So in terms of circuits, this might look something, and yes. These 4 boxes have now turned into a product, and these are all 2-body interactions, which we could decompose into C naughts and such. So the circuit might look something like this, right? You want this unitary, but what you have to do is approximate it as these kind of little steps in time. And to show kind of how this is an approximation, here I've done some just simple calculation where we have an exact evolution in black. And then we plot the trotter evolution for different numbers of trotter steps, 5 and 8. And you can see as we go from 5 to 8 steps, the red line more closely follows the black line. And this is kind of the general trend for trotterization and the idea behind there. All right, so this is how we're going to apply this is how we're going to apply dynamics to our quantum simulation. And when you do this, you'll plug it into a quantum computer, and let's say you have some state that's 1, 0, 0, 0, 0, which would be just one particle starting in the far left of that site, and we're going to see how it traverses the lattice. And this is how this would be this classical exact values you'd expect. But when you plug it in your quantum computer, you find out that you get this instead, which can be a bit frustrating if you're new to the field and you want to try to understand what's going on. And so this is because there's just noise on these devices. And and I would argue that although your results might start like this, if you apply physically motivated error mitigation strategies, you can get dynamics that match the real dynamics much closely. And that's what I'll show at the end here. I am getting short on time, so I might skip a few parts here. just going to highlight one error mitigation strategy, which I think is maybe the most important. And that is, let me back up just 1 second here. So in terms of error mitigation, it's good to think in terms of hardware, like what's the specific hardware I'm using? Am I using superconducting qubits, trapped ions, photons, like NV centers? What's the actual hardware? And then what is the problem I'm trying to simulate on there? Okay, so I'm going to highlight just one error mitigation technique and then move on. So this is what I like to call the true native gate set. A lot of times we talk in terms of C naughts and single qubit rotations. But when you actually talk to a hardware physicist who's working with these superconducting qubits, they think in terms of driving fields and evolving Pauli operators. They think of rotations like a ZX operation. And so if you can cast your circuit in terms of what's actually happening on the hardware, you'll get a very large improvement in fidelity right away. And so to highlight this, so I'm going to put a little X. Don't use C naughts. Use what the experimentalists use on the actual hardware. So to highlight this here in just 1 minute, for example, when we want to apply this Trotter step, we are going to need to apply this XX gate. And we might think, okay, well, here's how we would decompose it in terms of C naughts and just a standard gate set. But then you ask your experimentalist friend and you say, well, what are these C naughts? How are you actually driving these on these superconducting circuits? And they would tell you, oh, well, we're driving this ZX interaction for pi/2 time and wrap it with some single qubit gates so it looks like a C naught. And then you say, wait a second, that RZX looks a lot like this RXX. Why don't I just drive my RZX gate for a little bit and wrap it with some single qubit gates to make it an XX interaction? And sure enough, if you do strategies like this, your fidelity boosts dramatically, because for one, in this top circuit, you're driving twice and for a total of pi time. And in this bottom circuit, if you want to trotterize and just evolve for a little bit, so theta would be small, you're driving this 2-qubit interaction for a short amount of time, which means you have less error. And so you have fewer gates, shorter drive time. And I'm running out of time, so I'm just gonna close here with these last two plots, where here we've kind of we have an estimate for the circuit fidelity for various numbers of Trotter steps. So as we increase these Trotter steps, we have more gates. And you can see if you kind of naively just set up your circuit, your fidelity drops dramatically, but in terms of C naught gates. But if you force the quantum computer to operate in these native gates, your fidelity stays higher, stays relatively high. And you also save time, or as you can see here, the RZX optimized circuits here in red run for a short amount of time. So if worried about coherence and drifting, your circuit will run faster and have less noise in general. So I'm going to skip ahead these other strategies I talked about and just say that I want to share this plot here on the right, where if you combine error mitigation techniques in modern devices, you can actually get dynamics that faithfully represent what you're looking for. It's represented by these red data we got off IBM device. So with that, I want to thank you for your time and leave it open for questions.
Well, thank you for your presentation. So now this is where anybody who would like to ask some questions would ask some questions. Let's see if anybody has any questions.
I've got one. Adrian, this is Terrell France. Thanks, AJ. You're kind of out of my league here. I do social simulations, and anyway, wouldn't a transpiler, I mean, in most classical programming I do, certainly not circuit building, the compiler does a lot of that homework for me. So will the transpilers be making these adjustments for me, or down the road?
Yes, great question. So at this point, your regular old transpiler, particularly in Qiskit, it will not do this RZX optimization out of the box. That being said, though, you can And in our notebook, we show you how to tell the transpiler, you kind of have to help it a little bit. You have to say, hey, it's hard for it sometimes to identify that a circuit that looks like this. Sometimes it's hard for it to know that this should be shown as what I've shown here at the bottom right. And so there are functions you can pass to the transpiler specifically and to have it do these specific kind of optimizations. But at this point in the story of quantum computing, you have to tell it specifically, and it's not kind of a out of the box option. And that's one reason why we wanted to write this paper in this notebook, as well as to show that these options are available if you look for them.
Yeah, thanks. I'd imagine as time goes on, these sort of things will be built in and perfected, and me as a circuit designer won't have to deal with it.
I would hope
time.
so. I would hope
Yeah.
so. That I think the one hard part, though, the one hard part is that most algorithms are written in terms of C0 gates.
Yeah,
And
exactly.
you need kind of these pairings of C0s to get this real advantage here. So, but this is something that I personally would like to work on in the future, and I think is a really promising avenue. Yeah, and thanks, Terrell.
Great, thank you.
Okay, well, I would like to point out that we ask, before we get started, in general, we ask 5 questions of every presenter. So AJ was the first presenter, thank you. I was told that you are an excellent teacher, and this is absolutely clear, so thank you. This was
Okay.
wonderful. And so this was really a great presentation. Now, we asked 5 questions of every presenter, and for the sake of the recording, I'm going to mention roughly what they are. There are 2 questions where we say, number 3, where we say, can you enumerate your top 3 dream employers, companies that you'd very much like to work for or intern with, or any other plans that you have for the future? And the last question is, do you have any questions, literally any questions, any kind of questions that you might want to ask of any of our industrial partners? Now, today seems to be an unusual situation. But in general, there are industry members here. So for the sake of the recording, since we are trying to, we actually do have an office hours program, and it's fairly big. And normally Christopher Bishop, who runs it, shows up here, but he is not here. Who knows why? For the sake of, we also have in plan to join somehow Quantum Marketplace with the e-poster sessions. This is what AJ's response was. But unfortunately, I don't think there will be any industry member right now that could give us any feedback. So Terrell is the current chair of the TAC. Jake, who's the vice chair, was supposed to be here, but somehow he couldn't make it. Celia, who is the executive director, couldn't make it either, and so on. It doesn't matter. But he says, after graduate school, I plan to accelerate quantum hardware capacities in industry, particularly gate and qubit performance. I would be happy to do this in a trapped ion company in the United States, such as Quantinum or IonQ. I've also loved my time with IBM and would be happy to work there again. Okay, so the reason we ask is not necessarily, in the past, this really was a significant question because people who would come here from small companies would get an idea whether their companies are known, anybody mentions them or not, right? Because everybody knows the big companies. But this was an opportunity for smaller company, let's say Vescent Photonics or Montana Instruments, or whatever small company you can think of, for them to realize that people who are ready to work in industry may or may not think of them. And so we got an answer from AJ, and I'm going to move shortly to the second presenter. Last question, where I said, do you have any questions? He says, and then there's nobody here to answer the question, but I promise to pass this question to the industry members and see what we're going to do with that about the answer. How might the emerging quantum industry fare in the current upcoming economic turmoil? So this is a very serious and significant question. And normally there would be at least Charles Robinson from IBM Quantum that would immediately take a stab at this question. But as far as I can tell, right now, we don't have any industry members unless
Well, yeah, venture capital is drying up quickly. No,
Unless
we can't.
505 is an industry member, but that's a phone number, but I don't know who that person is.
This is Jake.
Oh,
Douglas
Jake, how
from
are you? So
India.
Jake
Yeah.
is here. Okay. Okay, now let's move to the second presenter, if that's okay with you. I'm going to share the screen and show you the screen again. And after a brief introduction, we're just going to listen to the presentation. So here's now the screen. And I'm going to say that our second presenter is Carolyn Ten Holter from the University of Oxford's Responsible Technology Institute. The Institute looks at ways in which technology can be deployed that recognize the need to consider societal impacts. Carolyn's background is in industry with legal and business development experience. She's currently investigating responsible quantum computing and AI as used in autonomous vehicles. The title of her presentation is Bridging the Quantum Divides, a chance to repair classical mistakes. So Carolyn, go right ahead. Thank you for coming here today.
Well, thank you very much for the invitation. Hopefully you can all see my screen now. My talk is radically different from AJ's because I'm coming at quantum computing from a social science perspective. Although I work in a computer science department, we look at the ways in which quantum computing has the bigger picture. So we talk to industry, we talk to policy. We're very concerned to investigate the ways in which quantum computing might impact on varieties of communities across societies. So the title Bridging the Quantum Divides is actually taken from a paper that I'm going to talk about in a minute. But I thought I would start just by introducing the team here at Oxford. We all work on responsible quantum. We've just started a new project, which is what the hyperlink is for, looking at responsible communication around quantum computing. You know, we're all very aware of the problems of hype. There are kind of views and thoughts out kind of in the wider world about what quantum computing means. People are relatively familiar now with Shor's algorithm, the idea that quantum computing might break existing cybersecurity and so on, even though, you know, everybody in the cybersecurity industry knows that a cryptographically useful quantum computer is still a long way away. But so these ideas are out there, and one of the concerns we have is that there's going to be a societal pushback against quantum computing because people will have these very negative associations with it. That's one of the things that we think might be a challenge. And kind of the guiding principle is this quote from a former research participant: for people that are on the brink of building a world-changing technology, you should think seriously about what you're doing. And that's really the kind of the guiding principle of responsible innovation. So the Responsible Technology Institute is underpinned by principles of responsible innovation. So that is looking at questions of impact, talking to wider communities of stakeholders, and really trying to engage in a dialogue with society about, let's collaboratively decide together what kind of future we want to build together, and let's then figure out how we get there, rather than focusing on where we think the technology could go and just going there without really considering what the impacts of that might be. So the reason I wanted to talk about the Bridging the Quantum Divides paper is because it kind of illustrates some of these points quite nicely. So this is the paper. The citation is there for anyone who wants to look it up. And our starting point was the speed with which quantum computing has accelerated over the last few years. We all know that, you know, this is a hard problem, right? Even though it's all largely engineering now, it's still really hard. But with the number of countries now having quantum programs. A colleague actually put a list on LinkedIn, and it's everywhere now. Australia, Canada, many European countries, India, Israel, Japan, Russia, South Korea, and obviously, China and the US and so on. Everybody's doing this. And so there are colossal sums of money going into it, even though we know, venture capital has been, is starting to look a little bit less plentiful than it was. Governments have been putting enormous sums of money in because there is this recognition that quantum computing has this huge value to the economy and to society. And that is largely calculated in terms of dollars and pounds and yen and so on, rather than kind of societal benefit of other kinds. So in order for society to get these benefits of quantum computing, citizens want to know that it's being done right. They want governance. And at the moment, there is none. There is no regulation that governs the quantum computing space. Other quantum technologies that are a little bit more towards the industrial development end are, they have their own kind of governance structures. Quantum computing, who knows? But in order for societies to trust this technology, we need to have governance structures of some kind in place. And I stress that I'm not necessarily talking about legislation or regulation. There are lots of different kinds of governance. You can have things like industry standards, where government is investing in the technology. They have governance structures in place for those investments. So there is oversight. We all know that when we've had research grants, you have an enormous amount of paperwork to fill in and reports to write and so on, which is all part of those governance structures. So this is what we're talking about when we think about the way in which this is done. So needing to kind of reassure people that these developments are being undertaken in the right way, in a responsible way. We talk about responsible innovation. And this is very much about working with, as I was saying earlier, wide communities of people. So stakeholders, we're not just talking about end users, we're not just talking about the public. And, I do see some frustrations from quantum computing developers thinking that we are so far from end use that, talking to publics, talking to citizens there's so much you'd have to explain that it doesn't really make any sense to be engaging at this point. But we're not necessarily talking about end use cases. We're talking about stakeholders, and that can be other industry partners, that can be policymakers, that can be other scientists in the same sort of field. Here at Oxford, we're pulling together the Oxford Quantum Institute, which is people from physics, people from computer science, people from materials, people from robotics, to try and have these kind of cross-disciplinary conversations to talk about not just how the technical challenges work, but how we can collaboratively develop this. And so when you have those conversations with people, when you move up, particularly outside your own research field, and this is why, coming at it from a social science perspective is so interesting for me, you think about some of these concerns in a wider way. And because the technology is still so early in its development phases, there is still time and space to respond to concerns. This is still something that can be guided. If you compare it with perhaps something like AI, to a large degree, that's out there, that's gone. And some of the problems that we've been seeing, some of the reputational damage that has been done to big companies where they have perhaps unwisely lent too much on AI systems. Let's not have that happen with quantum computing. Let's not be getting to 2030 and looking back and thinking, wow, I wish we had done that differently. So let's have these conversations, let's respond to these concerns as we go. Let's think about societal impact, let's think about people's need to trust the technology, because that's a very present concern for people. So in the paper, we were very focused on this question of access to quantum computing. And when you're engaging with society, you start looking at who has access, who doesn't. And even with present systems, I think just smartphone usage in the US, more than 80% of the population has a smartphone. In Pakistan, that is less than 20%. So fewer than 1 in 5 people have a smartphone. And when you think about the impact that would have on people's access to opportunity, people's access to education, people's ability to kind of participate in international activity, even at a national level, there's a huge impact there on the economy of a country and people's life chances, all of these different things that just simple access to computing power can offer. And what we kind of see starting to happen with quantum computing is it's a very expensive technology to develop. It's kind of aggregated in state-owned research facilities, in big companies. This is not something that is currently accessible to many. And as much as anything else, we see nation states developing their own kind of quantum strategies that have a very nationalistic feel. People want to grow their own and keep their own. They want to keep their own researchers, they want to keep their own research. Here in the UK, we have something called the National Security and Investment Act, which is all about who you can accept money from in your quantum startup or your spin out. And there are countries where if you accept investment from them, the government is going to look at that investment and may potentially repudiate it and say, no, you have to give that money back, because they don't want that nation having a stake in what's regarded as a British quantum computing company. And this goes against the grain of where quantum computing has kind of grown up. You know, it's been a relatively small community. It's been very collaborative across national borders. And as I was saying earlier, and we all know, it's still really hard. There are still really hard problems to solve. And so people need to collaborate. So these kind of nationalistic approaches where nobody's thinking about, well, how about we share some of this with the global south? How about we improve another country's kind of economic chances? Because, then a rising tide lifts all boats. This could be good for everybody. So we looked at some of these issues, and we came up with a few recommendations. This was a very brief kind of thought piece paper, but we looked at some of the initiatives that are underway at the moment for trying to improve access to quantum computing. So IBM has a system, for example, where it is trying to increase education around quantum issues. Amazon obviously has Breakit. A lot of these things are kind of online, but they're not enough. Individual philanthropic initiatives or companies trying to train up the next generation of their future employees by allowing them access to their quantum systems, which is one way to go about the capacity shortages, certainly. But it's not enough. We think there needs to be international agreement and collaboration on these things, because these are not going to be computers that you have on your desk. There are only ever going to be probably a handful of them. They're difficult to build, they're going to be difficult to maintain. Countries are going to have them, big companies are going to have them. Let's figure out ways in which we can make this a benefit for everybody. And we see the need for public and private sector cooperation, partly because of the governance question that I was talking about, but also because research that goes on in private companies tends to be held within those companies, and whereas publicly funded research tends to be public. That's not an absolute rule, but that tends to be the kind of direction of travel. And we want to keep collaborating. We want to be able to talk to our friends in Europe and in Canada and in Australia and in the US, and be able to solve some of these challenges together without kind of worrying about whether it came from the US or whether it came from Germany or Finland or Japan. So we work with the World Economic Forum, and they have developed some governance principles, and we see that every country that has a developed quantum computing program also has people working on these kind of collaborative, responsible innovation approaches. So we see that as a very positive development, and I'm very well aware that these kind of topics are wildly different from the sorts of things you normally discuss at these forums. But I'm very grateful to have had the opportunity to come along today and talk about it. And I'm aware that I'm running out of time, so I will leave it there.
Any comments and questions? Thank you so much, Carolyn. Any questions or comments from anybody? Yeah.
I've got one. This is Terrell.
Go
Thanks,
ahead.
Thanks, Carolyn, for the presentation. This is a constructive question. I just don't quite know how to say it exactly. So quantum is a pretty small technology in any way you look at it, quite frankly, nearly any way you look at it. And it's really, the social issues are just as present in much more omnipresent technologies like AI. And so in workforce training, for example, in quantum, the difficulty is not training people in quantum. The real macro problem is training people in STEM, particularly in the United States, maybe definitely not nearly as much in Europe, but in the United States, where the problem is a huge problem and quantum is just a small thing. So we've got AI, we've got, every person on the planet needs a phone now, and quantum affecting our social lives, at least in our lifetimes, is going to be pretty small. But that doesn't mean you shouldn't study it. How do you see, like, let's say you guys, you folks at Oxford and the community figures the secret sauce of how to have socially acceptable quantum computing out there in the world. It's just a small piece of a larger puzzle. How do you see anything we learn in this quantum work you're doing helping to inform or improve the bigger problem of, technology and its effect on society as a whole? How do you see going from the micro to the macro?
Well, one thing about doing this work in quantum is that you're doing it in real time. I mean, I have just finished my doctoral thesis, and while I was writing it, things were moving so fast. Quantum has developed in so many ways in just the last 3 years. So it's been amazing to look at how society, how industry, how policy responds to a novel technology, and how policy is made for a novel technology, and seeing some of the mistakes that have been made with other novel technologies. And as I was saying, we have this opportunity to get out kind of in front of the train with quantum. But the approaches that we can use for quantum, that we can develop in an agile kind of governance sandpit way, we can use those for other technologies as well. In fact, the UK government has developed an office for AI, looking at responsible and trustworthy AI. And some of that is based on this responsible innovation work that we have been doing in quantum computing. They have finally realized that AI needs some kind of centralized governance. And as I say, not necessarily legislation and regulation, but some kind of governance structure. And so, although quantum is a small case, potentially, it can, the work we do in quantum, because it's all moving so fast, can really inform work on other novel technologies. We talk to people developing 6G systems and telecoms. And again, these kinds of structures, this kind of responsiveness, this engagement with people, trying to talk to societal stakeholders, those kind of modalities really help with other technologies too. So, quantum might be a small use case, but it can be really helpful kind of when you look across the board.
Yeah, it's a good point. We're trying to get ahead of the storm here. Thank you.
So, for example, all right, first of all, thank you so much. And indeed, the type of presentation was a little bit different from the others, but we decided that we are going to have one presentation of this kind every time. The question for Carolyn was, can you enumerate top 3 dream employers and so on? She mentions Quantinuum because she says Elias Khan has a very good handle on topics of this kind, but she also says that in terms of where I see myself being able to have the most impact, probably in policy work. So I regret the fact that Corey Stambaugh is not here. He is the Senior Policy Advisor and Industry Liaison for the National Quantum Coordination Office at the White House Office of Science and Technology Policy. And he has been a very active member of this TAC in the past. I want to mention 2 things. So the title of your presentation in the paper was Bridging the Quantum Divide. And there is divide, let's say, between 2 companies that would like to work, but they can't on account together because they are in different political spheres of influence. And we've had situations of this kind. We have to be careful how to approach a company, let's say in China, if we are coming from the US. That's one type of policy, but there is a second aspect that I was thinking originally that has affected us in this particular context with e-posters. And that's, there is a divide because we cannot offer opportunity to everybody. So there's been significant work last year and the year before to make sure that, say, big companies like IBM reach out to historical Black colleges and universities and provide them with enough information and materials so that they can have the same opportunity as other universities and students that have, let's say, more money. There was a significant and concerted effort to reach out to historical Spanish-serving institutions. And I think they've been somewhat successful, but not as successful as they would like to be. And I remember last year there was an announcement that there was a company that could build a 25-qubit quantum computer for you in 30 days. And it wasn't even that expensive. But what was expensive was the fact that they were using superconducting qubits. So you had to have a very expensive refrigerator, which almost nobody could afford. And we are working on establishing what exactly recommendation we could provide for, say, computer science departments if they wanted to have a lab, a hardware lab for quantum. And it's basically completely out of reach of any computer science department to try to build a 3 to 5 quantum computer at this time. Undergraduates can probably just calibrate computers. And if they wanted to build something, they probably could just build qubits. If they chose superconducting, there is a good aspect to all of this because you could work with a system such as Qiskit metal. And the reason we are talking about quantum computing right now is because IBM first put stuff on the cloud. And you could almost build the hardware and then hope that you can ship it to a foundry. And if there is enough money, then they could build it for you. And so the argument has been made, why do you even want to build it? And the answer is, I don't necessarily want to build it if I'm in school. I want to learn how to build it if I work for them later. But if I want to do outreach, I'd like to build my own materials. So I can then take them with me to a high school and show them how to do it. So there's a divide in terms of opportunities that we offer to communities. And also there's a divide in terms of how much money and resources you need. MIT has far more opportunity and ability than even, let's say, a university as mine. That was just a set of comments that I really value your presentation very much, and thank you for being here today. And if anybody has any other questions for Carolyn? If not, we're going to go on the third presentation, and this would be Manuel Humberto Muñoz-Arias. He did his bachelor's in physics in Colombia and then moved to New Mexico, where he did his master's and PhD at the Center for Quantum Information and Control at the University of New Mexico. I would like to share the screen now so I can show you one more time the title of the presentation. I lost it, I guess, but maybe this is for the quantum processor that I mentioned before, that it can be built in 30 days. Here's the list of presentations. So the title of Manuel worked with Ivan Deutsch and Pablo Poggi at the University of New Mexico. He works in quantum measurement and feedback control and applications in quantum information science. He's currently a postdoctoral fellow at the Institute Quantique in Sherbrooke in Canada, working with Alexander Blake. So the title is Phase-Space Geometry and Optimal State Preparation in Quantum Metrology, which essentially is results regarding quantum sensing. With this, thank you once again, Manuel, for being here. I'll stop sharing. Would you please start your presentation?
All right. Hope you can hear all well. Yeah. So yeah,
Yes.
thank you for the introduction and the invitation. Yeah, as mentioned, I'm currently at the Institute Quantique, and the work I will be presenting today was done while I was at the University of New Mexico in Sherbrooke, together with Pablo Poggi and Ivan Deutsch. And if at the end you would like to know a little bit more details, I encourage you to look at a preprint we posted in the archive recently. So I will be telling you how you can exploit phase-space geometry tools to characterize some state preparation protocols in quantum metrology. And so the initial question here is going to be, why state preparation? And the answer is rather simple. Is because non-classical quantum states are resources for quantum metrology. And by this, I mean that having a non-classical state allows you to have sensitivity of some apparatus that is better than what you will have otherwise. And now a paradigmatic example of this is advanced LIGO. And the ingredient that allowed LIGO to become advanced LIGO is the injection of a squeeze vacuum into the interferometer. So phrasing it in the terms I'm talking here, it means that this non-classical state of light, which is a squeeze state, allows you to have a sensitivity of this interferometer that has improved over what it would be otherwise possible. And for me as a theorist, the interesting question here to ask and to explore is, how can I find then strategies that allowed for a rapid preparation of these non-classical states? And suppose you have found one of these strategies, then can we understand what is the mechanism behind this preparation speed? And can we generalize it and then maybe use it in other contexts? And I'm going to be talking about particularly state preparation, but when we think about quantum metrology, right, state preparation is only a stage within a whole scheme. So let me start by telling you how a usual quantum metrology scheme goes. So again, you start with your initial state that undergoes some time evolution up to some finite preparation time, and then you get your non-classical state, after which you get a secondary evolution that is that we are going to call the sensing evolution, which imprints the value of this unknown parameter mu into some observable property of your system. And then you make a measurement of this property and learn something about this unknown parameter. And what I'm going to say for the rest of the talk is I'm going to set conditions on the last two stages of this protocol that I'm going to allow me to focus only on the first part. And in particular, I'm going to be focusing on the situation where the physical system of interest is a collection of spin with one-half particles, like the kind of things that you have when you have trapped ions on an ion trap, or when you have ultra cold atoms cooled down in a cavity interacting with one of the like modes of your cavity. All right, so these two conditions are going to be the following. First, I'm going to assume that there is an optimal measurement that extracts the maximum information about my unknown quantity, and that this can be performed. And this is going to, in principle, maybe allow me to saturate the quantum Kramer-Rao bound of sensitivity. And the second condition is going to be that we are going to assume that the unknown quantity mu is encoded as the precession rate of these spins in the presence of an external magnetic field. And what that means is that the generator of the sensing evolution is one of the components of the collective angular momentum that you construct as the addition of the individual angular momentums of each of these particles. Now, with these two conditions set, then the problem, again, reduces only to a state preparation. And what we are going to look at is families of Hamiltonians that we are going to use to prepare our non-classical states, and how long it will take for this evolution to reach a given target state. And we're going to quantify the performance by looking at the metrological gain of the quantum Fisher information, a quantity defined by this ratio, where the denominator is the quantum Fisher information that you calculate as the variance of your generator. Now, when you think about this quantifier, there's usually two limits that people would like to compare the performance of their strategy with. One of them is the standard quantum limit given by metrological gain equals to unity. And this is saying that whatever strategy you have is not doing any better than what you could do with classical resources. So in a way, no quantum enhancement there. And in the other end, you have the Heisenberg limit, which is telling you that whatever strategy you have is performing as good as it is possible by what it is allowed by quantum mechanics. And oftentimes this limit is unreachable. And what people look for is to have a metrological gain that exhibits Heisenberg scaling. And by this, I mean, we have in denominators some positive constant that is guaranteed not to scale with the size of your system. Now, the goal will be then to have a strategy that generates small values of this metrological gain in the shortest time possible. And the question is, how are we going to do this? And this has been answered. And the answer is to use nonlinearity. So we are going to focus on families of collective spin Hamiltonians that have terms which are nonlinear functions of the components of the collective angular momentum. And in order to analyze this, as the title of my talk suggested, what we're going to do is to exploit the geometry of the phase space. So let me tell you a little bit more about collective spins and their associated phase space. So again, a collective spin model is a description of this collection of atoms using a single collective degree of freedom. And the most general Hamiltonian based on these operators that you can write looks something like this. The important point here being that this Hamiltonian conserves the total angular momentum. And what that means is that whatever phase space representation you construct, quantum or classical, is guaranteed to have the time evolution constrained to the surface of a sphere. Now, as a side note, the type of product states that I'm going to be my initial state are known as spin Coronian states, which physically can be understood as you have all of these spin one-half particles in your collection that being polarized along the same direction. Now, the classical phase space representation is constructed by taking the thermodynamic limit of the Heisenberg equations of motion. And this gives you the state of your system being described by three classical numbers, X, Y, and Z, the components of the mean angular momentum, and the evolution given by a phase space flow. Now, you can learn a lot about the structure of this phase space flow by looking at the stationary points of this evolution and the stability given by the eigenvalues of the Jacobi matrix evaluated at the fixed point. Now, for Hamiltonian flows, as it is the case here, there are two deep types of stationary points. They can be either stable, which means the point is surrounded by periodic trajectories, or they can be saddles, which means you have two principal directions, one of which is being exponentially contracted and the other one is being exponentially stretched. And in the situation when you have an additional saddle point in some other spatial location in phase space, you're going to see that these branches, stable and unstable, connect different saddle points, and they are going to define separatrix lines. And the message here from the type of motion that points along these branches execute is that the separatrix is an exponential instability. And this will be very important for us in a couple of slides, so keep that in mind. Now, let me tell you how you can use these tools that I just described to analyze a particular nonlinear collective spin Hamiltonian that is known to be useful in quantum metrology schemes, that is called or known as the two-axis counter twisting. So it's given by two quadratic nonlinearities along perpendicular axis that I have chosen to be along plus 45 and minus 45 degrees on the equatorial plane. And so now a state preparation looks like this simple evolution that I have written here. I'm going to polarize all my spin 1/2 particles pointing up in the Z direction, evolve under my Hamiltonian up to some final preparation time, and hopefully get a non-classical state. One might ask then, what is a good notion of the best preparation time? And this, of course, depends on what is your target state. And something nice for us in this work is that it is known that this Hamiltonian allows for the rapid preparation of some metrologically useful states whose names are here. The important message here being that they all exhibit Heisenberg scaling, so they give you very good metrological gains. And how long it takes for the evolution to reach each of these target states is a time that scales logarithmically with how many spins you have in your collection. And the last question I'm going to try to ask here today is going to be, what is the origin of this logarithmically short preparation time? And in a way, we have already seen or hinted at the answer, which is the branches of the separatrix going out or into unstable points. And for this particular Hamiltonian, one can show some special properties, which are local optimality, whose geometric meaning is that the separatrix branches are orthogonal, and global optimality, with the geometric meaning being that the separatrix branches define geodesics on the sphere. And one can go one step further and actually put this into a more formal footing by making a mapping into the time evolution saturate in a quantum speed limit, then giving a better kind of like argument in favor of the optimality of this Hamiltonian. But I'm not going to give those details here. If you're interested, I'll encourage you to look into our work. Now, what we are going to do then to show that, in fact, with this simple geometrical picture, you can have this logarithmically short preparation times is I'm going to place my spin coordinate state in the north pole of the sphere. It has some quantum projection noise represented by some uncertainty patch. And I'm going to look at a single point at the border of this uncertainty patch. And I'm going to calculate how long it takes for this point to go from this initial position here all the way to this other position over here on the right. And you can go and do the calculation and you find an expression like this, where now, given a target state, you can go and see what is this final coordinate that you need to plug into your expression. And I can give you two examples here in red and blue. So in blue, we have the preparation time that it takes for this evolution to reach the optimal spin squeeze state. And in red, we have the time that it takes for this evolution to reach the non-classical state that minimizes the value of the metrological gain of the quantum feature information. And notice that they are both logarithmically shorter times in the size of the system. So in fact, we have by direct computation verified that it is the exponential instability of the separatrix and the geometry of this curve, the responsible for these short preparation times. However, one might have here a complaint, right? Because in a way, these expressions were computed by complete classical means. There were no quantum calculations involved. And you might ask, well, these are formally correct in the limit of having a collection of spins that have infinitely many spins, but this is never the case in any finite size experiment. So are they still good when you consider your system far away from the infinitely large case? And the answer is yes, you can go and do full calculations of these two metrological gains, calculate what is the time of these peaks, and compare that with the value that you get from this expression. That is what is shown here on the right-hand side plot. And we see that even for systems as small as 10, which is very far from the thermodynamic limit, these expressions that were computed by completely classical means are still giving you the correct preparation times for these non-classical states. And with this, I'm just going to summarize. The main message that I would like to communicate here is that thinking about the phase space geometry allows you to map a problem in the time evolution of quantum states into a problem that is only concerns with the geometry of curves on the surface of a sphere. And this is a very powerful tool that you can in principle use to make claims of optimality or suboptimality of any collective spin Hamiltonian. And we also laid out some interesting connections to the phenomenology of quantum phase transitions. Again, if you're interested, feel free to look at the preprint, or if you want to have more of a discussion, I'll be happy to talk to you. Send me an email. I will again thank you for the invitation. I will take any questions.
Are there any questions from anybody?
This is Terrell again. Thank you, Manuel. I've got a few terms I need to look up. I never really, I've been interested in metrology for a while as part of the quantum studying I'm doing, and haven't really thought about the state preparation. I'm not prepared to ask a question, but I'll make a comment. It was something I learned a few weeks ago, the importance of calibrating your measurements can't be undersold in that, you know, the United States Air Force has this stealth bomber, the B-2 bomber, and I guess it's been around maybe a decade or two that it's been in existence. And the only crash that ever occurred was the in that plane was the 5 sensors that are used to determine the height of the plane, or the, you know, the, I forget the term for it, but distance off the ground. And the reason that plane crashed is the initial state of 2 of those sensors were incorrectly calibrated before the plane took off because there was a little moisture in the sensor. So the sensors themselves were calibrated, but incorrectly. In other words, their initial state was wrong. And that actually caused the only crash that plane's ever experienced. So, you know, that's a tangible story, true one, about, you know, the importance of state, getting the state prepared right, as you say. I don't
I
know
think-
how much that has to do with what you're saying, for
Yeah,
sure,
no.
but
No.
it is an important point.
Yeah, no. I actually like thank you very much for the comment, because it brings up a very important question and a very timely question, especially given this what people like to call the noisy intermediate scale quantum devices era that we are currently in, right? So when I say in my talk that, oh, okay, so I want to live in theory land and only focus on the first part, on the first stage of this kind of like abstract description of what a quantum metrology protocol looks. I'm making assumptions about how well I can do the other two. And the big assumption is I can do them perfectly. And that, of course, fails for the current devices that we have. In particular, for the measurements, I'm saying, on one hand, I know what the optimal measurement is, which means I know what is that I need to measure to extract the maximum allowed information per measurement. And I know that I can perform it. And those two are gigantic ifs. And again, one could also make another talk only focusing on the third part and saying that usually and very, very generally speaking, the optimal measurement is either known, or if it is known, is really hard to implement. So there is another whole area of quantum metrology that is devoted to, okay, I don't have access to the optimal measurement. I can measure something else. How can I maximize the sensitivity of my scheme given the measurement that I can actually perform? And that is indeed a very timely research subject, especially given the type of devices to which we have access right now. So thank you very much for the comment.
Just to check my vocabulary, how does that, is that Fisher information that you're talking? You mentioned it. One of you mentioned it. Is that Fisher information? Quantum?
Yes.
Yeah,
Yes.
okay, got it.
I
Thank you.
think Tyler has a question.
Hi, Manuel. I really enjoyed the talk.
Thank you. It's nice to see you,
curious.
Tyler.
Yeah, it's good to see you too. I was curious if there's any connections between your work and this recent paper that just came out, this improving quantum metrology with scrambling paper. I don't know if you've seen this. If you haven't, just put it in the chat. I don't know. It might be, I thought you might just have seen it. I don't know. No big deal. I'm curious if you just have top of your head related. Closely related, or
I'm not sure. I'm not sure.
Okay.
The only thing that comes to my head, like right now, is that, well, again, scrambling can be described as a unitary process, right? That takes an initial state that you could call, quote unquote, a sort of classical state or a product state, and maps that into a highly non-classical state. So in that sense, I will say that you could, right, like whatever you put here during the state preparation, I don't see why it couldn't be a quantum evolution that gives you scrambling. And maybe that non-classical state, I mean, not maybe, given that there is a paper about it, I assume that the non-classical state that results of that is metrologically useful.
cool. Yeah, thanks.
Thank you. Thank you for the question.
Okay, so this gives us, first of all, an opportunity to thank Manuel once again. And we are now going to transition to the last presenter. Before I do that, for the sake of the recording, I want to mention here a question from Manuel for our industry partners. And the question goes like this: could you list the top 3 skills that you value the most when you hire a theorist for your quantum team? So this, for Terrell, this would be a really good question to ask and collect information from all the members, and then share with students.
Yeah,
But-
that would be an interesting discussion question, no doubt.
Mhm. There was a similar question from Carolyn that was, I would like to ask them whether any of these points resonate with them, the points in her presentation, and to what degree do they consider societal acceptability in their work? That's another important thing that I think would be good to know. So with this, once again, thank you, Manuel. I'm going to share the screen for the sake of showing the title. The last presentation is by Tyler G Thurtell. The presentation title is Optimizing One-Axis Twists for Realistic Variational Bayesian Quantum Metrology. And while I'm introducing him, I'm going to stop the sharing the screen so he can share the screen. Tyler is a graduate student at the Center for Quantum Information and Control at the University of New Mexico, working with Dr. Akimasa Miyake, that group. His research focuses on quantum sensing and NISQ algorithms with influence from quantum many-body physics. Please go ahead, Tyler.
Okay. Thank you for the introduction. So I'm going to tell you all today about a project I recently completed with my advisor, Dr. Akimasa Miyake, about variational quantum metrology. We have a preprint on the archive. The number is down here. And if you're interested, I'll also have the number on the last slide. So the setting we're considering is that of quantum sensing or quantum metrology. So the setup will be similar to what Manuel has just showed us. Our general goal is that we'd like to estimate some parameter phi of a quantum channel as precisely and accurately as we can. The way we're going to think about doing that in this talk is beginning with the all plus state, and then we're going to send the all plus state through some noisy quantum channel, which we'll think of as an encoding. That will result in us having some probe state. Following that, we'll send this probe state through some free evolution channel, which depends on this value phi we want to estimate, which will then make state depend on the value phi. Following that, we'll send the state through some decoding, which will again be a potentially noisy quantum circuit. And following this decoding, we'll always have it end with a global rotation about the x-axis by pi/2, followed by what you can think of as a computational basis measurement. We'll then post-process all of the output of that measurement into an estimate of this value phi, such that when averaged over measurement outcomes, the estimator is proportional to the sum of the expectation value of Pauli Z on it. One of the things that will be very important throughout this entire talk is that we'll consider this channel we're trying to estimate is just a rotation about the z-axis by some angle phi, plus possibly some noise channel. So I want to say that there's two paradigms that people generally think of in sensing. And the first one is the entanglement-free paradigm. So I have a whole bunch of probes here, and I send them through the channel to be measured all independently. And the second is the so-called entanglement-enhanced sensing. And in this setting, I will first allow my probes to interact in some way, bring them apart, and then send them through the channel, let them interact again, and then finally they'll be measured. And the idea is that during these interaction periods, they can become entangled with one another. And this can allow our sensing to be more precise and more accurate. But we don't just want to think about what sensing we can do in principle. We want to think what we can do with some particular set of resources that could be realized in some particular device that hopefully is available now or in the near future. So that kind of restricts and makes the problem more complicated. We also want to worry about the effects of noise, which might even be device specific. And we also want to tailor our strategies for sensing to any prior knowledge we might have about this angle that we're trying to estimate. One paradigm for addressing all of these complications that's emerged recently is that of variational methods. So you can look in these, for example, these 4 papers I have in the lower left, if you want some introduction. These are sort of the early works of these, of this type. But the idea is that we're going to replace our encoding and decoding procedures with parameterized circuits. So a parameterized circuit is a quantum circuit in which the gates depend on some classical number that we want to then optimize, possibly with feedback from the actual device to make our sensing strategy as good as possible. And while this is a promising procedure or promising avenue, it's very new. And so a lot of work is still needed in terms of analyzing which parameterized circuits we should use and understanding how effective they are and how robust they are to noise. So that's where we come in. In this paper, we introduce a new family of parameterized circuits for this problem and theoretically analyze their effectiveness and their robustness to noise. So the pieces that we're going to build our parameterized circuits out of are global rotations and one-axis twists. So both of these are defined in terms of total angular momentum components. And so total angular momentum component is just 1/2 the sum over the Pauli operators in some direction summed up over every single. And then a global rotation is just generated by a single total angular momentum component. And a one-axis twist is generated by the square of a total angular component. I want to note here that all of our entangling resources come from the one-axis twist, which generate sort of global icing-like interaction. And I also want to note that there's a permutation symmetry in this in all of these operations. This permutation symmetry is important because it simplifies our simulations because we can restrict to the n+1 dimensional symmetric subspace. I also mention it because we're going to break the permutation symmetry later, but for now we have it and it's helpful. So we call the family of parameterized circuits we introduce arbitrary axis twist circuits. They're illustrated in the bottom left here. You can see that it's sort of a one-axis twist and 2 rotations, and then we kind of repeat this pattern. We abbreviate these by AAT-MN when we use for the member of this family that uses M encoding twists and N decoding twists. And generally speaking, you can think that what these implements are effectively an alternation of one-axis twists about arbitrary directions and rotations in arbitrary directions. I want to compare this approach to a family of parameterized circuits that were considered previously for this problem in 3 papers that are down in the bottom left corner here that were very inspiring and motivational for us in pursuing this line of reasoning. And so we refer to these as parity symmetric circuits and abbreviate them PAR-MN. They're illustrated here, and you can kind of see that instead of 1 twist and 2 rotations, they considered 2 twists and 1 rotation. The general idea and the reason we call these parity symmetric circuit layers is that the generator of each gate is required to commute with the product of Pauli X on every single qubit, or the X parity operator. And the reason this is a positive thing to do is that it guarantees that when you average your estimator at the end of the procedure over measurement outcomes, it will be anti-symmetric about the angle you're trying to estimate. And this is, this is positive because we would like these estimators to look as much like lines as possible because they're just trying to, as a function of the angle, because they're just trying to give us the exact value of the angle. When we compare the number of one-axis twists per parameter here, we see that if we look at PAR 2M2N, it has about half as many parameters as AAT 2M2N. And so this is sort of a trade-off between the power of increased entanglement and the power of increased freedom of rotation direction. Okay, so I've told you we want to optimize our parameterized circuits. There's one more piece that I need to tell you about if we really want to set up an optimization problem, and that's a figure of merit or an objective function. To set this up, we take a Bayesian statistics approach to the problem, which is to say we treat phi, this angle, as a random variable and use a prior distribution for it, denoted by p sub phi. We always take this to be a Gaussian distribution with mean 0 and standard deviation delta phi. And then we define the Bayesian mean squared error to be this big delta phi squared, which is given by this formula. And if you look, it's essentially the mean squared error at a given value of phi averaged over our prior distribution. And then the figure of merit we take is the ratio of big delta phi to little delta phi, which quantifies essentially our uncertainty after the measurement relative to our uncertainty before the measurement. Okay. Oh, there we go. So the first thing we did then is numerically optimize our arbitrary axis twist ansatz in the absence of noise and for just a few one-axis twists. And so the results are shown in this figure here. On the x-axis, we have the standard deviation of the prior distribution, and the y-axis is our figure of merit. So the things to notice here are the blue curve, blue circles demonstrate what's possible without entanglement. The downward facing pink triangles show what's optimally allowed by quantum mechanics. And in between, we see that the first big improvement is given by these green triangles, which occur when we add a single encoding twist. And then the next big improvement is these red diamonds, which happens when we add a single decoding twist on top of the encoding twist. And then the next big improvement comes from the brown crosses, which occurs when we add an additional decoding twist. So this is AAT 1-2. This indicates to us that once there's a single encoding and decoding twist in use, you're better off to add your entangling resources to the decoding, at least one axis. So next we look at the effect of increasing the number of twists used in the decoding. And so here we go up to 5 decoding twists. And while we do see improvement with the number of twists, we also observe that there is diminishing return, indicating that at least in some settings, you may not want to strive for the absolute optimal performance. You may be better off limiting the number of one-axis twists you're using and just getting the improved performance that you can. And I also want to note that these types of observations line up well with things that were previously observed in the context of the parity symmetric circuits. So next, we compare more directly with the performance of the parity symmetric circuits. And so we see that in the two-twist regime, our arbitrary axis twist circuits can lead to some improvement. For example, our AAT 1-1 seems to outperform the PAR 2-2 setup, and the AAT 1-4 setup seems to perform comparably to the PAR 2-6 setup. The next thing we did was try to study the effect of noise in the free evolution stage. In particular, we wanted to study the effect of spatially correlated noise. But as I mentioned earlier, the spatially correlated noise is a problem for us because it breaks the permutation symmetry that we were using to facilitate our simulations. Our solution to this problem came from matrix product states and operators. I think in the interest of time, I probably shouldn't go into too much detail about this. But just to give you a very rough idea, we tried to simulate things for as long as possible using symmetric subspace techniques or techniques closely related to symmetric subspace techniques, and then only map things to matrix product states when we absolutely have to at the very end. And the effect is that as long as the noise model has an efficient matrix product representation, the entire process can be simulated in polynomial cost. Okay. So the spatially correlated noise that we actually ended up considering is a correlated dephasing channel. So now, during the free evolution, rather than every spin being rotated by the same angle phi, each spin is rotated by phi plus some random amount that is different at each site. These random R sub j's are taken to be Gaussian random variables with mean 0, and covariance is given by this equation. So in particular, C1 is the variance at each site of these R sub j's, and C2 is the covariance between adjacent neighboring sites. And then we took our arbitrary axis twist, for example, 1-1 strategy that was, using the circuit parameters that are found to be optimal in the absence of noise, and studied the robustness of that strategy to this noise. So in particular, on the x-axis here, I'm showing the covariance between adjacent sites, and the y-axis is the variance at a single site, and the heat map is showing the R figure of merit. And then, of course, I should say these black curves indicate lines of constant values of R figure of merit. So our observations from this are that the correlated noise is not significantly worse than the uncorrelated noise in terms of loss of performance. And in fact, we observed improved performance in the presence of anti-correlated noise. Our explanation for the origin of this improvement for the anti-correlated noise is that at the end of the day, we to some extent have a separate estimator for each spin, and our total estimator is the average of the estimators for all spins. So if our error on this spin and this spin are sort of anti-correlated, we expect that there could be some cancellation of the errors. Next, we study the robustness of these strategies to circuit level noise. In particular, we consider the effect of gate dephasing on single qubit dephasing after each one-axis twist on each qubit. So again, we take the strategies we found to be optimal in the absence of noise and see how robust they are to this type of. And so on the x-axis, I'm plotting the probability of a dephasing error in a single one of these dephasing channels. And on the y-axis, I'm plotting our figure of merit. And the key observations from this plot are that which strategy performs best actually depends on the noise strength. And in fact, by the time we get down to p is 10 to the minus 2, we see that actually the AAT12 strategy is the best one, outperforming all of the ones with deeper decoding circuits. And we also see that, well, another way of thinking about this is that this enhances the diminishing returns with depth that we previously observed. And so with that, I will stop and see if there are any questions. And say thank you.
Thank you. If there are any questions, this would be the time to ask them.
I have a comment. This is Terrell. Just thank you, Tyler. You gave me a lot to chew on there. I had trouble following a lot of it. It's out of my wheelhouse, but I'll take a look at the slides and think about them later. Thank you.
Thank you.
Anybody else?
I have a question.
Manuel.
So Tyler, you mentioned that having deeper encoding and decoding eventually ends up being like stops giving you advantage.
Yes.
And why is that? Like intuitively, I would have assumed that if it is longer, like you keep doing better, right?
Right. And we do observe that you do continue to see improvement. It's just that the amount of improvement you get for each additional twist seems to be smaller. I mean, so for example, the amount of improvement between when we use one twist, so this red curve, and when we use 3 twists, so the orange curve, versus when we use 5, which is the blue stars on this plot, is much smaller, right? And I don't know, we're not exactly sure why. I mean, to some extent, it may just be that you are approaching the optimal and you have to sort of target very particular strategies to really get down to this optimal curve. And those are just hard to exactly find when you're doing this optimization or when you're limited in the resources you can use. It's a good question, but we're not exactly sure.
And if you don't mind me asking another question.
Sure.
So the other question is, I think it's very interesting that the most improvement, like point number 1 here, right? So does this mean that the most important part is the measurement and the state preparation is not really that important?
No, I don't think I would say that. I think it could have something to, so we tried to choose resources here that are, resources people consider in using in the experiments. And I don't think it's necessarily that. I think it's potentially more that these resources are very good at the encoding, in the sense that it's been previously observed that in this setup where you're trying to essentially optimize this Bayesian mean squared error, that good probe states, spin squeeze states are good probe states. And one-axis twisting is good at making spin squeeze states. And so in that sense, I think it's not too surprising that that you don't need as many of these resources in the encoding.
Thank you.
Yeah.
Okay, well, any other questions? So if there are no other questions, I am going to say thank you so much to AJ, Carolyn, Manuel, and Tyler for coming here today. I think we're going to have this recording process available tomorrow. When I'll post it, I'll email you and let you know. And for everybody who is watching us in this recording, join us next time, March 21st, when we have our next session. Thanks again, and have a wonderful rest of Tuesday.
Thank you all, and thank you, Adrian, too.
Thanks, everyone.
Bye-bye.
Thanks.